I'm going to be eroding these surfaces to bedrock with just a thin coating of sediment. I'm going to have a thin coating of sediment down here in the valley, not as built up as it was during the Bahada stage. And now I have these thin plateaus with a little bit of sediment, and these are called pediments. So you'll see those terms whenever you read any geology that has to do with landscape development. And there's kind of a sequence to how this develops. And you can kind of look at it and figure out where you are in the sequence, what the relative age of these features are, just by kind of looking at it. First of all, you're going to have that downthrown valley, you're going to have this Horst and Brabant system develop. But then, very quickly, as the walls of that fault plane start to erode back, you end up with these deep slot canyons cut back into the plateau. Resistant rock on top, protecting the weaker rock down below. And as these areas now, these canyons expand, you have remnants of this plateau kind of out in front of the main plateau. And when they're large, they're called mesas. A little smaller, they're called buttes. And finally, even as the buttes get to be small, they're called pinnacles or chimneys. So the smaller these things get, from plain to plateau, in Spanish, in some parts of the southwest U.S., they call them esplanade. Mesas, buttes, and pinnacles, it just says, hey, this has been sitting here and eroding longer and longer and longer, older and older and older. So you can kind of get the sense of a relative age sequence here. Monument Valley in Arizona is typical of this kind of a situation. If you look here, here's a mesa, here's the plateau back here, here's a butte, you can see some buttes here, you can see a pinnacle right there. This area is probably one of the most filmed areas in the world. It's probably been in every great B Western. John Wayne made I don't know how many movies here, and you still see it in movies probably once or twice a year. It's a very popular area to go film for the Hollywood folks. So that's kind of deserts. So keep moving on here. And now I want to talk about life on Earth with you. A little bit of a creationist theme here, man and dinosaurs together. This would be the case, certainly, if everything was only 6,000 years old. And one of the pieces of evidence that is in the Creationist Museum in Kentucky to support this is a trackway, footprints in some fossil rock that are dinosaur footprints with smaller footprints right next to it that are interpreted, I quote, to be footprints of man, so that man and dinosaurs walk together. It's not quite that simple. It's very interpretive. They probably are dinosaur footprints, but they are certainly not man footprints. There are no really clear prints. They're probably, if anything, juvenile dinosaurs along with parents. But because of the way, they kind of slumped in as the footprint was left, they have taken on a little bit of a human form to them. So the creationist folks like to interpret them as man-made footprints. But we're looking at dinosaurs that really ended their reign on Earth about 165 million years ago, and you're looking at us who've only been here about 3 million years. So there's a little discrepancy in between us being able to walk with the dinosaurs. But that seems to be kind of one of the themes. So if you look at it, we've really got a lot of geological time to deal with, 4.5 billion years. But it's really only been the last 560 million years, the last half billion, that has really seen a big explosion of life on Earth. The first life that we see goes back to 3.8 billion, but it's simple, single-cell type of bacteria. And we see that as the prokaryote stage, where it's just really simple bacterial type of life. It shows up in the forms of algal mats, such as these stromatolites. And even though stromatolites are still with us today, they're very, very rare today. But back in the Cambrian and Precambrian, they were all over the place. They were the form of life, essentially. And they start out as an algal mat doing photosynthesis, get buried in a little sediment. Ooh, that shuts off access to light and photosynthesis. So the algal mat grows up through the sediment, forming a new mat to continue its photosynthesis. So we get these layers of algal mat, sediment, and they end up growing up into these kind of mushroom-shaped forms. So these are some of the earliest life that we see on Earth. And remember when we talked about Earth's atmosphere, we looked at how we really didn't see oxygen starting to accumulate on Earth until about 2.5 billion years ago. And that's due to the photosynthesis that we see, primarily things like algal mats, these stromatolites. The next step is much more complex. Eukaryote cells. I mean, now we're talking about cells that are organized. They have internal parts that have specific functions. And now life can really start to get complex. And this appears right around 2.5 billion years ago. And hey, isn't that about the same time oxygen starts showing up? How about that? Must be a connection there someplace, huh? Probably. So really the first life on Earth that we can see is about 3.8 billion years ago. Pretty simple blue-green algae. Then we see oxygen getting into the atmosphere. Oh, it starts a little before 3 billion years ago, but really starts around 2.5, and that's where we see eukaryotic cells being formed. And by the time we get up to the Cambrian, all of a sudden we see sponges and jellyfish and flatworms. In the Cambrian, boom, things take off. The number of species, just mushrooms. The places that life grows and lives, just mushrooms. Habitats and niches just explode. So the Cambrian now is the big boundary as far as geology. Before that, we don't see much life that's, very, well, I don't mean to say meaningful, it's all very meaningful, but it doesn't tell us a lot of information because it's so rarely found. But one of the places that we see this happening is up in Canada, and it's a place called the Burgess Shale. And here's an outcrop of it. You can see it's a pretty rugged area over toward the Vancouver part of Canada. And it's this outcrop that used to be the edge of a reef back during the Cambrian. And reefs are fantastic places for all sorts of different life forms. And this has been a section that was discovered back in the 1930s and has been worked every season since then practically. And it's still producing all sorts of interesting details of what happened back in Cambrian times and how life started to evolve. During the Paleozoic now, we basically see the first appearance of life that has hard forms, hard parts, things like shells. So that starts to show up. And for the most part, these are creatures that lived in fairly restricted seas, fairly protected areas. And we see things like trilobites, cephalopods, these coiled shells, sponges, and corals all kind of make their first appearances during this time. So if I was to look at the ocean in the Paleozoic, this is kind of what I'd see. I'd see these corals, I'd see these trilobites, I'd see these cephalopods here, all these kinds of things. Here's some trilobites there. So I start to see a very different sea than what we see today, but the beginnings of life up there. So what we see during the Paleozoic, from about Cambrian up to about 250 million years ago, organisms just dramatically diversify. Things get really weird and really start to just blossom. Insects, plants move onto the land. Wow, I mean, think about it, that's a big, big change. We see lobe-finned fishes adapt to the land, they become amphibians. That's a pretty magnificent change. And in the Pennsylvania, we see these big tropical swamps that develop, and these become the coal deposits that we exploit today. Some of the first land plants look like this. This is a Mississippian silitum from 430 million years ago. And this is what one of those Pennsylvanian age swamps around 318, about 300 million years ago, would have looked like. Not exactly what a swamp today would look like, a whole bunch of different type of life, but still you wouldn't mistake it for being a swamp. But at the end of the Paleozoic, something happens. There is a majorly mass extinction. I mean, it was perhaps as close to life being wiped out on Earth as we've got. 70% of all the vertebrate species, all the species with vertebrates, were wiped out, taken off of the land. 90% of all the marine organisms gone. So I mean, this was a significant event of some sort. So this Permian extinction is kind of the one that we still haven't figured out. What happened? And after we made the connection between the end of the dinosaurs 65 million years ago and a meteor impact having been a major factor in that, if not the cause, they started saying, this Permian extinction, maybe there was a big meteorite strike then. The problem is we haven't been able to find the smoking gun. If we had such a mega impact, where's the crater? That we haven't been able to tie in. So that's still kind of part of the hunt. Another thing we see are a lot of volcanic eruptions about this time. But there's nothing definitive to tie the mass extinction and the amount of volcanism going on together. So we're still trying to figure this one out. But obviously, the big smoking gun needs to be found if it's been a meteor impact. But that's kind of the leading hypothesis at the moment. Dinosaurs basically rule the Mesozoic. They're there from Triassic, Jurassic to the end of the Cretaceous. They basically ruled for 160 million years, and then within 100,000 years, poof, they're gone. Now, 100,000 years sounds like a long time, doesn't it? Geologically, it's nothing. It's instantaneous. So why, after 160 million years, the dinosaurs disappeared? Well, we knew they were in trouble. There were 2 or 3 different types of dinosaurs that were already either extinct or on the verge of extinction. Triceratops, ankylosaurs, pretty common ones, actually. And then we think we see this meteor impact, the strike happening, and it just took them out. The Mesozoic is often called the age of reptiles, because this is when we just see dinosaurs rule and things really take off. But organisms that survived the Permian extinction at the end of the Paleozoic, man, they just begin to diversify and go all over the place. We get gymnosperms. These are, well, cycads, conifers, and ginkgos. Conifers are pine trees, right? Trees with needles. And if you want to see a ginkgo tree, They've been around since the Jurassic. We have one right here at the back of the building in the little sunken rock garden area. Go check it out. But they have these fan-shaped leaves on them. They're really cool. But ginkgo trees are still with us today. They're a beautiful, beautiful ornamental tree for gardeners. And this is when reptiles really become dominant land animals. And they evolve very rapidly at this point. So here would be kind of a tropical area. These would be cycads. And these kind of are still around today. This would be a picture of some modern ones. And of course, the large carnivorous dinosaurs became kind of the thing we all focus on when we think of this time. The herbivorous dinosaurs like the Apatosaurus, we used to call them brontosaurus. The pterosaurs, the big flying reptiles, and Archaeopteryx, which was kind of this small chicken-sized dinosaur that walked around on two legs and had feathers. And this guy, as it turns out, was the ancestor to modern birds. So every time you throw a chicken on the grill, you're really kind of barbecuing up a really old dinosaur.
That makes it even better.
Yeah, man. Mammal's revenge. But here in Chicxulub, which is this little town sitting there in the Yucatan, somewhere 65 million years ago, it appears there was a meteorite here. And we can see evidence in the rocks all through this area. Most of it's buried under sediment and other rocks, but when we look at it from geophysical means, gravity, magnetics data, we can see the shattered remnants of that strike. And it is believed that that was the smoking gun. That was the meteorite impact that finished off the dinosaurs. The Cenozoic was next. And that's been essentially pretty much the last 65 million years for the most part. And this is a pretty exciting time because now we see mammals show up. And they replace reptiles as the dominant species on Earth. And we see two groups evolve, marsupials and placentals. Okay? We're placentals, kangaroos are marsupials. And some of these groups now become very, very large. Unfortunately, some of these largest mammals become extinct during the Pleistocene, during the last ice age. The Cenozoic can probably be best defined as being the period of flowering plants. This is when plants really take off and evolve. Angiosperms really become the strong influence, and evolution of birds and herbivorous mammals. This is where the Cenozoic really is defined and why things look pretty much the way they do today. The Quaternary period is the last 2.5 million years or so. And this is where we show it. And most of the evidence of us comes from the East Africa Rift Valley. And this has been an area that's been worked for years and years and years. And what we've seen now is we have evidence of man-like fossils going back. We've got them back now to 3.8 to 4.2, depending on how you interpret things. And we can see these pre-human primates coming all the way up through Anthropopithecus robustus. And then we start to see the ancestors of our species coming into finding Homo sapiens. The newest thing that's starting to show up, it always used to be thought that Neanderthals, which were kind of right before us in the evolutionary order, had died out and were completely separate from Homo sapiens. But now we're finding that these two groups actually intermingled, overlapped, and that Homo sapiens and Neanderthals definitely interbred. So